Hello, ladies and gentlemen. Good morning and welcome to Lorenzo's Lessons of Space. This here is episode number 5, and here I'll be talking about two concepts, and they are delta V and TWR, or thrust to weight ratio. Delta V stands for the change in velocity. The V is the velocity, and delta means a change in physics generally. Now, before I get into the nitty-gritty of the stuff, let me explain to you why it's been quite a while since the last video. And that's because I have moved to Malta. I got a job there and now I'm settled there. I have an apartment, and I sent my computer to me in the mail, which, as you might imagine, takes quite a while. I was quite happy though. I packed it all in bubble wrap and took some of the components with me in my airplane luggage and reassembled it on arrival. So that worked out quite well. And now here I am set up, and I have internet and everything, and I can continue making videos. I've made a few StarCraft videos in the past, and I'll continue making those as well. But I'm also going to continue making the lessons of space here. Here we are in orbit around our faithful planet Kerbin, and with just a sample vessel to demonstrate to you the concept of delta V. Before I'm going to do anything with this rocket, let me try and explain to you some things about it. Delta V, I already said, it means a change in velocity, and this is a very important metric in determining a rocket's performance, what it is capable of, what it can do, and what it can't do. Delta V is measured in meters per second, which is a measure that is also used for our speed. And the delta V is a measure that is a metric that measures a rocket's or a spaceship's capability to change its velocity. Because the V is the speed, it's in meters per second, and delta is a change in it. It's a change in velocity. Now, to help you understand why this is an important metric for a rocket, rather than something like maximum speed or range or things that are more familiar to you if you drive a car. If you do operate a car, you will be familiar with things of miles per gallon. How far does it get on a set amount of fuel, or its range? How far can it go on a fuel tank? And you might think range might be an important metric for a rocket, but it's almost useless, and I'll tell you quickly why. Because once you're in space and you're in an orbit or a trajectory that does not intersect anything, you'll just keep on going. So effectively your range is infinite, and your range is almost always infinite unless you're impacting something. Here in this trajectory we are in an orbit. The apoapsis, the highest point, is 2.5 million meters, so 2,500 kilometers, and the lowest point is at 135 kilometers. And as you might recall, the atmosphere here on Kerbin starts at 70 kilometers, so this orbit is quite stable, and the rocket will remain going around indefinitely. So the range, in effect, is infinite. That it has an infinite range does not mean we can get to all the planets. Its range is infinite, and Juno here, which is looks a lot like Mars in our solar system, is a finite distance away. Still, this rocket won't be able to get there. So, as you see, range is not that useful a metric. Excuse me. Something else, fuel efficiency, is very important in rocketry. It's called specific impulse, more accurately, but we'll not talking about that. We'll not be talking about it in this video, but in the next rather. Acceleration is also important for a rocket, but only insofar as you're not damaging your structural integrity or hurting your pilots. As long as the acceleration is within the structural tolerance, it's not that important. Usually in space, you're on long trajectories, you have a long time to apply your thrust. If it's a low thrust, you accelerate slowly, but if you do it for a long time, you reach the same speed because there's nothing in the way. There's no air holding you back. There's nothing holding you back, so you have a lot of time, even if you have a low thrust, to do it. So acceleration as a rate of time, so acceleration, like in a car, you can do like 0 to 60 in 5 seconds if you have a nice car, or 3 seconds if you have a really amazing car. Those kind of numbers are quite meaningless for a rocket. What we want to know is not what speed it can accelerate to, but how much it can accelerate, period. So, for instance, if this rocket has 1,000 meters per second of delta V, it means it can change its total velocity by 1,000 meters per second. Straightforward, isn't it? Now it can do this in a straight line, and then it will, for instance, if I turn on the engine, no, I won't turn on the engine yet. I will first fast forward to a higher bit in the orbit, so everything moves just a tad slower. Oh shit, I have a crash. Stop. So, my recording software had crashed. Anyway, here we are back again in the game. I fast forwarded time to the apoapsis of our orbit. We're quite high above the planet now, and we're moving at 667 meters per second. And I was just about to explain to you what delta v does. Say we have 1,000 meters per second of delta v. It means we can change our velocity by 1,000 meters per second. We can use it to accelerate to 1,000 meters per second in a given direction. What we can also do is accelerate to 500 meters per second, turn around and slow down to a stop again. Or divide this in any other portion and vector you wish. So just to demonstrate this, pay attention to our speed. It's at 666.5 right now. I'm going to add about 80 meters per second to it. So we light the engine, and we're at 740 meters per second. Now I cut it off again, and we added roughly 80 meters per second. Straightforward as can be. That's how you can measure your delta v. If we look at the map now, our orbit will have changed. The highest point is now 2,560 meters, and the lowest point is now 350 kilometers. So we can say that to raise the lower point of this orbit from 130 kilometers to 350 kilometers from an apoapsis of 2,500 kilometers takes about 100 meters per second in delta v. And these kind of measurements are important because by doing this, by charting how much delta v it takes to get into a certain orbit, or to get to the moon, or to land, or to brake, or to take off, and for every destination there is a delta v cost. And knowing that delta v cost, you can calculate this using math, or if you're a Kerbal, just work it out experimentally. So for instance, we could add another 60 meters per second in our prograde direction, taking our speed up to 800 meters per second. So let's do that now. And there we go, a little bit more. And we're at about 800, and we can see our orbit has raised even more. It's 580 kilometers now. So using science and math, we can work out how much delta v is needed for a given maneuver. And that allows us to, when building a rocket or designing a rocket, to know how much fuel and how much rockets we have to bring. Because the beauty of the delta v measurement is that it's, once calculated, completely independent of the rocket. You can have a small rocket with 2,000 meters per second of delta v capacity, or budget as it's often called in rocketry, or you can have a massive battleship-sized behemoth of a rocket that's also capable of 2,000 meters per second delta v. And when you have these two, you know they can do the same mission profile. They can attain the same orbits, they can attain the same trajectories as one another can. Of course, they will need different amounts of fuel and different amounts of structure and different amounts of engineering to reach the delta v budget. But once you calculate it, you know what the rocket can do and what it can't do. And that's really why delta v is used a lot. To calculate delta v, I'm not going to give you the math because that's not my thing, but you can go into Google and Google for the rocket equation, and it's that easy, and then you get it. And the terms it takes are the mass of the spacecraft, the fraction of fuel of that mass. So it takes the mass of the spacecraft completely full with fuel, with a full tank, and it takes the mass of the spacecraft completely empty. So then it knows the amount of fuel that is then it knows the fraction of your spacecraft that is fuel. And the other term it has is the specific impulse of the fuel, which is again the efficiency term, which determines how much fuel is required for a given impulse or push. And we will be talking about this in the next video. So I hope I've given you a fair understanding of delta v now. Let's just max out this rocket here. You see there's a little bit of fuel remaining, and see how far we get. So we started at 666 meters per second, and we exhaust the fuel at 1,017. Disregarding the slight changes because of varying orbital altitudes, we end up at the delta v capacity, leftover capacity of this rocket of about 350 meters per second. And as we can see, the orbit has changed again. So we know now that to get from this orbit back down to the orbit we had, we need 350 meters per second of delta v. Sadly though, this rocket is now completely empty, and Jurgen Kerman, the guy that is in here, will have to stay in space either until he figures out a way to make more fuel, or until someone comes and gets him. So we leave him here, and we move to another thing I have made to talk to you about TWR, the thrust to weight ratio. And before I'm going to do that, I'm going to talk a little bit more about delta V and taking off from a planet. What I talked to you about was delta V in a space environment. In a vacuum, there's no resistance, and every meter per second of delta V you apply will go into a new vector, into a new course. On a planet, of course, while taking off, that's not so. There's air in the way, and you have to climb up against gravity. Delta V is still an important measurement. It will still, for attaining an orbit from a planet, there will be a delta V budget. For instance, for taking off from Kerbin, I believe the delta V budget is about 4,000 meters per second. If you have that, you can attain an orbit around Kerbin. That's quite a generous budget. You can do it with less, but you need good flying. And you need good flying then because delta V is not quite so straightforward when in an atmosphere. For instance, the gravity here on Kerbin is 9.8 meters per second squared. And that just means that any object that is pulled towards the planet will be pulled towards the planet at that rate, at 9.8 meters per second. Notice that's the same unit as our delta V metric is, per second. So if we apply just enough thrust to hover, to not go up, not go down, we expend 9.8 meters per second of delta V per second. Notice that this delta V is lost. It's not going into the speed of the rocket. The rocket will remain at the same space, at the same location, while it's expending delta V. It's hovering. And we call this gravity drag. And if we increase the thrust and we start going up, say we increase thrust to twice that of the gravity, say we increase the thrust to 19.6, no, that's got to be, 19.6 meters per second, we will be going up at the rate of 9.8 meters per second, but we'll also be losing the same amount in gravity drag. Gravity is not the only thing that's holding us back. There's also the atmosphere, and the amount of delta V loss from the atmosphere of course varies with rocket shape and speed. So to calculate the total amount of drag of delta V lost in an ascent is quite a complicated matter, but for now it's just enough to be aware that it exists. And this is where thrust to weight ratio comes in. Thrust to weight ratio is basically what the words imply. If your rocket weighs 100 kilograms and you've got 100 kilograms of thrust, your thrust to weight ratio is 1. And with a thrust to weight ratio of 1, you're not going to take off, you're going to hover. Because you can apply just enough force to not fall down, but there's no force left to push you up. So for having a rocket that takes off, you always need to have a thrust to weight ratio greater than 1. A thrust to weight ratio lower than 1 isn't enough to take off. It might slow your descent, and maybe if you have parachutes as well, it will help in that, but it's not enough to take off. This rocket here I made intentionally with a thrust to weight ratio of about 0.98, so it's just under 1. So when we fire the engine and release this clamp at the same time, it will slowly fall down, really slowly, because the thrust is just not enough to support its own weight. But of course you have to keep in mind, a big part of the rocket is fuel. So as the fuel is burnt, the weight decreases, the thrust stays the same, so the weight of the rocket falls, the thrust to weight ratio climbs over that 1 mark, and the rocket starts to climb again. I'm going to launch it now, let's see what it does. So there, it's going down just a little bit, touches the ground, and then as the weight reduces, it is going back up again. See, beautifully, very, very slowly. And as it is doing this, just wait a second, I have to reduce the volume here, the sound is so loud. So let's go with that. Yeah, loads better. So as it is doing this, it's burning fuel, it's expending delta V, at least it's expending about, I would say, 10 to 12 meters per second of delta V per second, yet our speed is only increasing by about 2 or 3 meters per second a second. So in ascending this way, really, really slowly with a very low thrust to weight ratio, you are expending lots and lots of delta V to get into the air. Way more than you need to. So unlike when you're in space, when it doesn't matter how quickly or how slowly you apply the thrust, it does matter when taking off from a planet. Note also that of course the thrust to weight ratio is dependent on which planet you are on, because it has to do with the surface gravity. If you're on the moon, a ship that would not be able to take off from Earth or from Kerbin would easily be capable of taking off from the moon, because the gravity there is so much lower. So the same ship there has a much greater thrust to weight ratio. For instance, if you look in our real world, if you look at the lunar excursion module, the lander, no way that could ever take off from Earth, no way. But on the moon it was no problem, because the moon has only a sixth of the gravity that we have on Earth. Note also that in space, where you're effectively weightless, your thrust to weight ratio is infinite. That's another way of saying it doesn't matter how much thrust you apply as long as you've got a long time. Because the thrust to weight ratio is infinite, all the delta V is going into useful speed, unlike here where almost no delta V is going into useful speed. This rocket here has about 1 or 2,000 meters per second of delta V, and at this moment we're going at 100 meters per second, and we've already exhausted more than half of our fuel supply. So a very, very big fraction of delta V is being wasted by fighting gravity drag, by just going up very slowly, because it has such a low thrust to weight ratio. It is important when launching rockets and building them to make sure they have a high thrust to weight ratio, always above 1, because otherwise it's just not going to go up, but ideally around 2 or even greater, depends a bit on the rocket you're making. So I think I made my point with this one, so I'm just going to abandon it. And I also prepared a different rocket that has a very high thrust to weight ratio. So like you see what that looks like. Of course, in this one it was losing so much delta V to gravity drag by just hovering, basically, that it was completely unrealistic. This rocket here does the other thing. It has a lot of thrust, so it spends a very low amount of time in the gravity well. It loses a low amount of delta V to gravity drag. Notice that the amount of delta V you lose to gravity drag is directly proportional. It's the same as the amount of seconds you spend in that gravity well. So if you take off faster, you spend less time in the gravity well and you lose less delta V. This rocket, I'll launch it for you and you can see what it does. It's got 3 engines and it's got roughly the same mass, only it got more engines. And it goes up really quickly. Oh, what the hell is going on? It also deployed the parachutes. That's not what we're planning to do, of course. Let's fix that and have a look again. Pro tip of the day, never deploy parachutes when launching rockets. It does not work great. So put the parachutes in the next stage and let's launch it. There we go. It goes up really quickly. Obviously it also uses fuel real quickly, and up until about in the first bit of its rocket journey it did really good in efficiency, but now not so much, because it's plowing through the air. It's so fast, it's creating the big drag visuals that are new in the latest version of Kerbal Space Program. Awesome game that it is. This rocket, even though you can't really tell, but I'm telling you so you can tell, it lost a lot of delta V going through the thick atmosphere. Because it was going really fast, it encounters a lot of drag. If you're in the car and you're going fast and you stick your hand outside, the air feels really thick. It's because you're going through a lot of it. And this rocket did the same, and it lost a lot of delta V that way. So, to quickly make a bridge into rocket efficiency and building strategy, a rocket that takes off efficiently does so at about 1 or 2 Gs of acceleration upwards. This means you need a thrust to weight ratio of around 2, and sometimes you need to manage your throttle, because you want to have a balance. If you go really fast, you have a low amount of gravity drag losses, but you have a high amount of air resistance losses. If you go really slow, air resistance losses are low, drag losses, they're low, but the gravity drag takes all your delta V. So you want to strike a balance where you're basically losing as much delta V to gravity drag as you are to aerodynamic drag. And this works out, after lots of math and models, to traveling at roughly the terminal velocity at your given altitude. On Kerbin, this translates to an ascent profile that is between 1 and 3 Gs. If you're doing that, you're doing well. So the rocket exploded because it ran out of fuel. I hope you understood what I was going on about the delta V measurements and the thrust to weight ratios and why they're useful and why they're important. I'm going to leave it here for the video. I can have a look at Super Satellite. I have no idea what that was about. Probably the leftover from one of my other videos. Yeah, I'm going to leave the video here. Next one will be about a specific impulse, and I will I will probably launch a rocket to some weird trajectory while explaining about that. Maybe I'll tack on some other concepts as well, but specific impulse for sure. Right, thanks for watching. Subscribe to my channel. I was saying in the StarCraft videos I was doing, I want to have some more subscribers to build my audience and to maybe live off advertisement income, but that's a bit hopeful maybe, but it would be nice. Anyway, so I decided to make some subscriber presents. At 50 subscribers, I will tape a camera to my forehead or do whatever, make an improvised helmet cam, and drive around Malta, the island where I now live. It's got some beautiful views, and I think you'll like it. And at 100 subscribers, I'm going to tape an underwater camera to my spearfishing harpoon gun and shoot you a video of me hopefully shooting a fish. And I have no idea, I've never done it before with a camera, and I have no idea if that's even gonna work, but it should be fun regardless. So once more, thanks for watching. This was Lorenzo of Lorenzo's Lessons of Space, and I'll be seeing you guys next time. Goodbye.